Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss the problems on the design of control memory. The first problem is the microprogrammed control organization has the following propagation delay times: 40 nanoseconds to generate the next address, 10 nanoseconds to transfer the address to the control address register, 40 nanoseconds to access the control memory ROM, 10 nanoseconds to transfer the micro instructions to control data register, and 40 nanoseconds to perform the required micro operation specified by the control board. So these are the various propagation delay times in the control memory. So what is the maximum clock frequency that the control can use, and what would be the clock frequency if the control data register is not used? So here this is the control memory architecture. There are two types of design of the control memory. One is the hardwired design of the control memory. Second one is the microprogrammed control memory. In the microprogrammed control memory, with the help of software instructions, the memory can be accessed. So here the microprogrammed control memory can have various blocks. The first one is next address generator, which is used to identify the location of the control memory. Next, this is used for address sequencing. Control address register is used to identify the location of the control memory. This is actual control memory ROM, and this the control data register, which involves the which carries the data that is used to place in the control memory. So here the next address information can be used to fetch the next micro operation. So this is the architecture of the control memory. Now we are having in the problem that is specified various propagation delays in each step of accessing of the control memory. So here the sequencer can take 40 nanoseconds, and control memory address register can take 10 nanoseconds. The ROM to fetch the micro instruction can take the 40 nanoseconds, and data register to fetch operand can take 10 nanoseconds. Micro instruction can be fetched in the 40 nanoseconds. So this is the clock signals that has to be applied to fetch the micro operation, so that address sequencer can be activated and execute the micro operation. So this is the timing diagram. Clock 1, in order to execute, it has to require the sequencer has to load the next micro instruction and the address from the address that is available in the ROM. So it has to require 50 nanoseconds to fetch the instruction, and to fetch the operand it has to require another 50 nanoseconds. So here the clock 1 has to be take the instruction in 50 nanoseconds, and in the next 50 nanosecond it has to fetch the operand and execute the data, execute the micro operation. So frequency of each clock can be for fetching the micro instruction and fetching the data it can be the 100 into 10 power minus 9. So it can be the 10 megahertz. If the data register is removed, so we have a single phase. That means the 10 nanoseconds in order to access the data from the data register. The 10 nanoseconds has to be removed for the instruction execution. So, what would be the clock frequency if the control data register is not used? So, the 10 nanoseconds in the instruction execution can be removed. So, it can be the clock frequency can be 90 into 10 power minus 9, 11.1 megahertz. Next is problem 2. The control memory of 1024 words of 32 bits each. The micro instruction has 3 fields. The micro operation field has 16 bits. How many bits are there in the branch address field and the select field? If there are 16 status bits in the system, how many bits of branch logic are used to select a status bit? Next, how many bits are left to select an input for the multiplexers? So, this has to define the micro instruction format. So, in the control memory, there should be 1024 words of 32 bit each. So 2 power 10 into 32. This is the control memory capacity. So the 32 bits are used to micro operation specification. So 16 bits. So here the micro operation field has 16 bits. Generally, the micro instruction can have 3 fields and 16 bits are used to specify the micro operation. And in this control memory address capacity is 1024. So, the address field can occupy the 10 bits. Total 26 bits are used and the remaining 6 bits can be used for select purpose. So, micro operation can consist of the 3 fields. Under this, 16 can be the micro operation and the address space capacity of control memory is 1024. 2 power 10 is the 1024. So, totally 10 address lines are required. So, 10 bits are used to reference the address space of the control memory. The remaining 6 bits can be used for the select. So, this is the micro instruction format. So, the branch address and the field of the selection field can use the 6 bits to specify the selection. Next, second bit is, if there are 16 status bits in the system, how many bits of the branch logic can be used to select a status bit? So, 16 status bits are there. 2 power 4 is used to represent these 16 status bits. So, 4 bits are enough to represent the branch logic. So, in the selection line, 6 bits are used. Under these, 4 are used for branch logic. How many bits are left to select an input-output for the multiplexers? So, here in the branch logic, 4 bits are used out of selection of 6 bits. Remaining 2 bits can be used for multiplexers. So, this is the solution for the second problem. The third problem is, the control memory has 4096 words of 24 bits each. How many bits are there in the control address register? How many bits are there in each of the 4 inputs shown going to the multiplexers? What are the number of inputs in each multiplexer and how many multiplexers are needed? So the control memory capacity is 2 power 12 into 24. So here this is 4096 words. So 2 power 12 into 24 bits. This is the address space of the control memory. So 12 address lines are used for the control memory. How many bits are there in the control address register? So here 12 bits are required for the address register. How many bits are there in each of the 4 inputs? So here 24 bits of each, 12 are used for the address. Remaining 12 can be used for the 4 inputs. So 12 bits are used for the 4 inputs. What are the number of inputs in each multiplexers? So 12 multiplexers can be used. So 4 by 1 multiplexers of each multiplexer type. So addresses of this input output selection for 12 bits. So 4 by 1 multiplexers of 12 can be used in the control memory. Next, using the mapping procedure, give the first micro instruction address for the following operational code. So A is the micro operation address 0010, B bit is 1011, C bit is 4 ones. What is the mapping process? So here the computer instruction opcode is of 4 bits can be mapped to the control memory address which is of 7 bits. So this is the mapping process. How it can be accomplished? The mapping process can be, what is the opcode 4 bits can be written as it is and which is having preceded by 10 and followed by 2 zeros in order to map to the control memory address of 7 bits. So this is called the mapping process. Now in the problem it is given 0010. So 0010, it has to preceded by 10 followed by 2 zeros. So 8 is the mapping process. This is the mapping address of the control memory. And B bit is 1011. 1011 preceded by 0 followed by 2 zeros. So which is having the decimal value 44. C bit is 111. 4 ones which is followed by 2 zeros preceded by 0 and equivalent decimal value is 60. So this is the mapping process. Formulate a mapping procedure that provides 8 consecutive micro instructions for each routine. The operational code has 6 bits and the control memory has 2048 words. So 8 consecutive memory micro instructions for each routine and opcode is of 6 bits and control memory is 2048 words. So opcode is of 6 bits, control memory 2048, address lines are 2 power 11 bits, 2 power 11 is 2048. So 11 bits are required for the address. But here opcode is of 6 bits. So these 6 bits opcode can be converted into 11 bits of the control memory. So that 2 zeros can be preceded and 3 zeros can be followed. This is the mapping process. Give the 9-bit micro operation field for the following micro operations. So here the accumulator value can be incremented, data register value can be incremented, PC value can be incremented, DR can load the memory location and DR can assign the value of accumulator DR value can be stored to the accumulator. So first we have to look into what is the micro instruction format. A micro instruction format of control memory generally consists of 20 bits. And these 20 bits can be divided into F1, F2, F3 are of micro operation fields. They determine what is the micro operations of the computer. And CD, which is used for control and branching logic. And BR, which is the branching logic. AD is the address field. So these 20 bits in total can be divided into F1, F2, F3 micro operation fields. CD, the condition for the branching. BR, the branching field. AD is the address field. The micro operation is divided into 3 fields of 3 bits each. So F1, F2, F3 each is of 3 bits each. The CD and BR each of 2 bits. The address is of 7 bits. So totally 20 bits. So this is the micro instruction format. What are the micro operations that are specified with the F1, F2, F3 fields? The field 1 micro operations are, so it is of 3 bits. So it is having 8 operations. So if it all F1 0 0 0 NOP, no operation can be performed. If it all 0 0 1 add operation can be performed. 1 0 clear accumulator. Next 0 1 1 increment accumulator. 1 0 0 so DR2 accumulator, the data transfer operation can be applied. And 101 DR2 AR register. Next 110 PC2 AR. 111 the write operation. These are the field 1 micro operations. What are the field 2 micro operations? The field 2 can consist of 000 no operation, 001 subtraction, 010 OR, 011 AND logical operation, 100 read operation, 101 AC2 DR, 110 increment DR, 111 PC2 DR. So these are the list of micro operations. Next, what are the F3 micro operations? F3 000 means no operation, 001 means XOR operation, 010 means complement, next 011 means shift left, 100 shift right, next 101 means increment PC, 110 AR2 PC, 111 reserve. So these are the list of micro operations available under the field 1, F1, F2, F3. So now how to represent these operations? So increment AC can be F1 field 0, 1, 1 and increment DR F2 field 1, 1, 0. F3 field no operation, so 000. And the second instruction can be the NOP, so F1 field 000. Next read operation can contain the F2 field 100. Increment PC 101 F3. Next micro instruction DR2 AC F1 100. AC2 DR 101 for F2. No operation for F3 000. So these are the binary codes used for the F1, F2, F3 in order to execute the micro operation. Next problem. Convert the following symbolic micro operations to register transfer statements and to binary. Read increment PC AC to DR, DR to AC, AR to PC, DR to AC, write operation. So what are the binary code equivalent for each field can be specified. So read. So here read can be the F2100 and F3 for AR to DR to AC. F3 can have 101. So here 001, 100, 101, F2, F3 fields can be performed in the binary, the micro instruction. Next, AC to DR, DR to AC. F2 you can have 101, F1 can have 100. And this F3 field can be no operation, so 000. Next, AR to PC, DR to AC, write operation. So here two operations from the same field, F1. So both uses the same field of F1. So this micro instruction can give you a conflict of execution. It is not possible. Next problem 8. Write the symbolic microprogram routines for BSA, that is branch and save address instruction. Minimize the number of micro instructions. So by using the micro instructions, the routine for branch and save address can be developed. So in the BSA, no operation. First it has to call indirect operation. Next it has to jump to the next address. That address can be saved. So PC to DR, AR to PC can be performed. Next jump to fetch. So write operation, that is address, written address can be saved, increment the PC. So branch and save address. This can be performed by saving the written address and incrementing the PC value. This is the routine. Next problem 9. The computer has the following binary microprogram. So instruction 60, which is having this length 61, 62, 63. These are the binary micro operations. Translate it to a symbolic microprogram as in above table. Fetch is in the address 64 and the indirect is in the address 67. So list all the things that will be wrong when this microprogram is executed in the computer. So 60 is clear AC complement. So jump to INDR CTS can be performed. 61 write and read, call the fetch. 62 add sub, return the next address 6360. And 63 is DR to AC and increment the DR. So similar 60, 63 locations can be used. So 60 cannot increment and complement AC at the same time. So here two operations has to be controlled on the same address. And 61 can also be cannot read and write, which is having the jump, but no saving of the written address can be taken place. 62 can also be cannot add at the same time the written address, the S bit value cannot be updated. 63 the map is executed irrespective of the Z or 60. And this is the reference that can be used to provide the solutions of the problems on the design of the control memory.
Like, share and subscribe. Hit the bell icon for more updates.